Hello everyone and welcome back. My name is Mr. Cobalt and in this video I will be going over collision theory. And so we're talking about collision theory with respect to reaction rates. And so in collision theory, for a reaction to take place, the reacting molecules must collide with one another. So on average, about 10 to the 9 collisions per second. So that's what collision theory is referring to, is this idea that in order for a reaction to take place, the reactants must collide with each other. Makes sense. It makes sense because atoms need to be rearranged, and if they're not going to collide, then there's really no there's no way for them to rearrange if they're not going to be in close contact with each other. So once the molecules collide, they may react together or they may not, right? So it depends on two other factors. So they collide. So this is going to depend on whether the collisions have enough energy in order to break bonds that are holding the reactants together, right? So if they just hit lightly and bounce off, there's no reaction going on. So unless the bonds break, reactants aren't going to rearrange their atoms. So you need enough energy for the collision to cause breaking of bonds. And it also depends on whether the reacting molecules collide in the proper orientation to form new bonds, right? So that's the other part of it. You got to make bonds and you got to break bonds. You got to collide hard enough to break the bonds, and you've got to collide in the right orientation to form new bonds. So this idea of effective collisions is also tied to the kinetic energy. That's kinetic energy factor, like how strong, how fast they're moving, how strong are they going to collide with each other. So for a collision to lead to overcoming that energy barrier, right, we're talking about that activation energy, right? So remember, you need enough energy to overcome that activation energy, right? And then part of that is the ability to make that activation complex. And remember, we saw before that the activation complex at the top of that curve, right? So you have that curve of the activation energy. And so in order to make it to the top there, you have to form an activation complex. And in order to form the activation complex, you need to be breaking bonds and forming bonds. But in order to do that, you need, one of the factors again is to have enough energy when you are colliding to overcome that energy barrier. So the reacting molecules must have sufficient kinetic energy so that when they collide, that activated complex can form. Okay, so that's what we're referring to. So you need enough energy to form that activated complex. And that activated complex, as we said before, is a transition state between reactants and products. And so the Arrhenius equation includes that term A, and we call that the frequency factor, right? But that frequency factor is made up of other factors. So the frequency factor can be broken down into two other terms. So that relate to these factors that determine whether a collision will be effective. And so you can see that the P value, so P and Z are the two factors. The P value is your orientation factor. The Z value is your collision frequency, the collision frequency. So when we're talking about collisions, when we're talking about orientation effect, this picture really does provide a way of seeing that clearly. So here we have two NOCl molecules, and these two NOCl molecules are supposed to react to form two NO molecules and one chlorine molecule. Well, the molecules have to align themselves to make and break the bonds, right? So in order to make chlorine, we need to form chlorine molecules, right? So if they collide in this fashion, if we're colliding with the two oxygen molecules, red is oxygen blue is nitrogen, and the green is going to be the chlorine. So if the two red atoms are colliding and they hit each other, well, that's not going to help make the chlorine bond form because they're on the opposite sides. Neither does it help to have a red and a green, chlorine and oxygen collide with each other, because once again, you need a bond to form between two chlorines. So this is not going to help. Here, this is actually going to help because the two chlorines are oriented towards each other. They're going to collide, and if the collision is strong enough, then that will help form the bond between the two chlorines, and at the same time weaken the bond or break the bond between the chlorine and the oxygen, the chlorine and the oxygen here. And that happens, you'll get your chlorine molecule and you'll get your two separated NO molecules, right? So that's what we mean by effective collision due to orientation. So with regard to effective collisions, continuing, collisions that lead to a reaction are called the effective collisions. That's what we mean by effective collisions, collisions that lead to a reaction. The higher the frequency of effective collisions, the faster the reaction rate. That makes sense, you know. So if effective collisions are those that lead to a reaction, and those you get a higher frequency of those collisions, then you're going to get a faster reaction rate. The collision frequency is also known as the number of collisions that happen per second. So the more collisions you have per second, of course, the more collisions can be effective and lead to product formation. So that makes sense. So if you have more collisions per second, then you're going to get more effective reactions per second, and that's going to lead to reaction formation. So for the orientation factor P, that is a statistical term relating to the frequency factor to the collision frequency. So we're relating frequency factor to collision frequency. Okay, so for most reactions, this p-value is less than 1. So generally, the more complex the reactant molecules, the smaller the value of p, which makes sense. If you have a really complex molecule, then you would expect that the likelihood of them colliding in such a way that that's going to lead to a reaction is going to be lower because they're so complex. For reactions involving atoms colliding, right, we have, so we're talking about atoms, not big molecules. If you have atoms colliding, then P is going to be approximately 1. Why? Because, again, P is a statistical term relating frequency factor to collision frequency. So single atoms are the ones that you are that are the simplest. They are spherical, so regardless of how they are oriented, they're always oriented in the right way. And so unless they don't have enough energy when they're colliding, they should form a product each time. So that's why the p-value is close to 1. Some reactions actually can have a p greater than 1. So this generally involves electron transfer. Okay, so here p is greater than 1. And again, for the orientation factor, the proper orientation results when the atoms are aligned in such a way that old bonds are broken and new bonds are formed. And so for most reactions, the orientation factor is going to be less than 1. Okay, so I'm going to stop there. I hope this was helpful in understanding orientation factor and collision theory. And if you like this video, like, share, subscribe, hit the notification bell for more notifications for more videos. Make a comment in the comment section. Let me know what you think and if you have any questions. And thanks for joining me. I'll see you next time.